All right, so thank you for the introduction. And I'm going to take our discussion one step further into the chip implementation, the physical design. And I'm going to talk about a technology, a specific technology of making our implementation more energy efficient by actually removing the clock from our pipelines. Pipeline is something that has been mentioned, I think, by almost every speaker so far. Pipelines exist in all levels, of the flow, of the hierarchy, and in the system level, in the architecture level. My focus is more on the microarchitecture level at the chip level, but maybe when I think about it, some of the ideas are applicable also at higher levels. Okay. So I'm going to talk about the concept of clockless pipelining, describe the design methodology, the way we deployed it into an AI accelerator, share with you our experience, our silicon test chips generations experience, talk a little bit about process variation and energy efficiency analysis, and something that has been mentioned, trading off accuracy with power consumption, and this is a cool feature which is part of this technology. So pipeline, as we all know, is a very common way of implementing or parallelizing tasks, and however, at least at the chip level, it has a cost that comes with it. It requires a very power expensive clocking scheme for synchronizing our logic. This consumes also area and a clock infrastructure and registers or other storage elements. So we are suggesting a method where we can essentially remove the clock infrastructure from much of the technology, save up to 50% in power, and on the way also save 12% in area. Before I get a little bit more technical, I would like to take an analogy, and as we are approaching lunch, I can't think of a better thing for that. So let's describe how a pipeline really works, why we need a clock, and why eventually we might be able to remove it. Okay. So assume we have a restaurant, a fast food restaurant, and we have a pipeline of preparing the tray, the dish, and it starts with a form where you mark what you want for the main dish, for the side dish, and for the drink, and this is prepared in a pipeline fashion. So in the first implementation, it's just one after the other. The main dish can take 3 to 5 minutes, the side dish 2 to 3, and the drink 1 to 2 minutes. Altogether, the duration is 7 to 10 minutes, so we can take an order somewhere in between every 7 to 10 minutes. Obviously, we can optimize this a little bit, and we can pipeline it. We can put a big clock in the kitchen and take the worst case preparation stage, and that's 5 minutes. And every 5 minutes, the tray needs to move from one stage to the other, but this requires clock and synchronization. If something goes wrong with the clocking scheme, so we'll have a mess. The lunch won't look so good. Maybe it will be kosher. It won't be very tasty. So can we safely remove the clock? Let's see. So we are suggesting a methodology which I would call WavePro Burger. And actually, the only thing that we need to guarantee that everything is propagating at a uniform rate. And at each stage, more than one tray can be handled. So altogether, this will take, at the worst case, 9 minutes, and at the best case, 6 minutes. And our essential claim that if this is the case, we can take an order every 3 minutes. because in such case, we will never face a situation or a case where an order is taking over a previous order. So everything works, is served in place. Can we optimize? Can we further optimize this? Okay. If our claim is that the throughput is only determined by the maximum minus the minimum total time, if we equalize them, that will be 0. This means that our throughput will be actually non-constrained. We can have an infinity bandwidth. Obviously, this will not work in reality, and not in a restaurant and not in a chip, because there is some uncertainty and variation. So we need to take some margin, let's say 10% of uncertainty, so we can serve the customers at 10% of the total time. That would be 0.9 minutes. And this is essentially the idea which is behind removing the clock. We want to equalize, we want to balance as much as possible. The long doesn't make sense, but this is what we want to do. Might not make sense. We want to make the faster stages slow them down, so everything is equalized, and then we have a balanced pipeline. Okay, that's for the popular science part. Back to silicon. We have applied actually the concept into maybe the most compute demanding or power demanding component in AI or in Accelerator, which is the dot product, the multiply accumulate, the inner product that has a lot of names, but essentially we want to do an element-wise multiplication. And the way we do it, we implement it with Wallace tree and fuse the Wallace tree, and it is a different. We're not doing one MAC at a time. We're doing multiple at a time. Let's say in our first generation it was 8 by 8 of 8 byte elements, and the second generation is 16. But it keeps feeding the building block, and it accumulates at the output. And this way we can handle big vectors. And what we have done here, usually such designs are implemented with pipelines in order to achieve a high bandwidth. So we have essentially taken out all of the registers. We've taken out the clock infrastructure. We launch the waves of information at a given frequency or at a given wave period, and we sample it at the output. We have a mechanism to tolerate process variation, which I will relate to a little bit more later. So in order to achieve this, we need to balance at the physical level, at the implementation, at the physical synthesis level. We need to balance the design such that all paths through the design have same minimum and maximum delay. This is the idea. I won't go into too much details into that because we don't have the time, but essentially we are using we are interacting with the commercial tools, and we are providing it with a good starting point, and then we fine-tune till we get the feedback, we iterate over it, and we fine-tune until we get a balanced design. Some of the advanced tools can do much of it themselves if we know how to provide the synthesis or the timing design constraints. But however, if we provide a good starting point, this will work even better. Okay, this is an example of the implementation at the place and route level. We have the sample stage, we have the accumulation stage. Obviously, balancing requires inserting delay elements. This is for the rough balancing. When we want to do the fine-tuning of the balancing, we manipulate the load of the wires by applying what we call as side gates in order to achieve a balanced as possible design. This is actually the way we've implemented it on our test chip. In order to do the analysis and the with the conventional implementation, included a conventional, traditional sequential implementation and our clockless wave-propagated implementation. And we have the same logic feeding the waves into them similarly. And this is the base for the measurements and results, which I will share shortly. This animation is based on actually true back annotation of timing. Each of the gray boxes represent a gate. It's not the way it is placed in the chip. It is placed on this chart on the timing window along the propagation delay. So to propagate the calculation takes 3 nanoseconds, but we can launch a wave every 1 nanosecond in this case, just to simplify it. And there are no registers, there are no latches, there is no sampling in between, there is no clock here. We've just guaranteed that the colored waves, each one of them represent a different calculation. They do not mess one with the other, and that's why we get a reliable result at the output. Okay, so how is this integrated into an accelerator? In our next generation chip, we have developed an infrastructure for acceleration, for hardware acceleration. We call it MaNNiX, Memory Attached Neural Network Inference Accelerator. It's targeting inference, and it's a test chip, so everything is scaled down, but essentially it has an on-chip memory, interleaved memory with a wide bandwidth to the accelerator. And we have 3 types of accelerators. This is we are not yet in the transformer area, which has been discussed a lot, but we have the convolution farm of accelerators, the pool, and the fully connected, which are the commonly used layers in many of the implemented networks. Since convolution, at least for vision use cases and so on, is by far the most compute consuming and power consuming, we have deployed or integrated the WavePro technology into the CNN engine. And the way it works is that we have in our memory, we have the feature map, and we have on the accelerator, we have 2 cubes. This is repeated in each accelerator, but we have essentially 2 cubes. One is for the weights, and one is which is stationed. This is weight stationed, is stationed in the accelerator, and one is for the sliding window on the feature map. The kernel is configurable, but in this case, it is hardwired to 5x5, a typical kernel. You can use less than that, but this is the choice we have made. And the depth is up to 6, but it also can be configured. At each cycle, we bring only the new data and bring it into the right place, into the input sliding window. And we don't need to bring the weights. It's convolution, they're already there, but we need to rotate both depth-wise and both in the height dimension in order to match the data cube. And we feed at each cycle, we feed a plate or a plane from the data and from the weights into the wave propagation, and achieve a bandwidth of the sock itself works as the sweet spot of this is all 65 nanometer, relatively an old process, but this is the commonly used in academy as a chip process, and we are bounded by the sock at 666 megahertz. However, we can achieve more than 10 gigamach per second just for one accelerator. Okay. In our first design, we focused on the core technology, and I mentioned the reference and the actual implementation. We can see on the scope the clock versus the data strobe and how they properly align. Okay, in our second implementation, we have integrated the entire accelerator, which I have described, including all the convolution, all the acceleration engines. Okay, so results in terms of energy efficiency. So essentially, power is proportional to speed, which makes sense. However, an interesting observation is that as much as the data is more sparse, the benefit is better. So when we have a 10% toggling rate, which actually correlate with sparsity, and as mentioned several times today, sparsity is a common feature in layers, especially as we go deep in the network. So we can save over 50% of the power. This is what we have measured in our wave-propagated, the clockless wave-propagated versus the sequential reference. If the toggle is 100%, meaning everything is changing every cycle, the data and the weights are everything, every bit toggles in the design, then the saving goes down to 30%, which is still substantial. If we look in energy efficiency terms, so we run the classic fashion MNIST through the network, which has multiple convolution and the fully connected layers, and the entire inference cost in terms of energy, 0.4 to 0.8 microjoule in the sequential, in the classic implementation, and 0.2 to 0.5 in our optimized implementation. Many times when this is presented, there is a good question about how do we tolerate process variation. This affects very much the gap between the minimum and the maximum. And the key for that is the delay tuning element. This is adjustable at field and post-manufacturing. We can actually place the strobe at the output of the pipe. We can place the strobe. We can control the point where we place it. And the nice thing is that this can protect both hold time and setup time problems. Usually, when your chip is too slow, or you're working at extreme operating conditions, or you want to lower your voltage, then you can handle the setup by just slowing the speed of the design. But you can't do anything about hold time, because if you violate hold time, this will not work. In this mechanism, since we care only about the window between the minimum and the maximum, we can place it at the optimal place. Okay, finally, this has been mentioned also, and this is a very interesting observation. In many cases, we are willing to trade off accuracy with energy. Sometimes, in some phases of our inference, we care less about accuracy, and a very natural way to do it is to reduce the voltage. This is a big impact on the power. If you reduce the voltage, then it will work to some extent, and at some point we'll start getting errors. And to some extent, we can tolerate the errors because the matrices are sparse, and if we get here and there some errors, the network will still converge into a reasonable result. And for example, if we are willing to reduce the accuracy by 10%, we can reduce the power by 25%. And more interesting, if we apply this principle, which is not something we invented, this is something which is known and done. But if we apply to a sequential solution, then we will hit the hold time wall. But if we apply it in our technology, we can go really down. Of course, reducing the voltage also means reducing the frequency, but we can still get reliable or useful results. This basically concludes my talk. The technology is integrated, as I mentioned, into by now into 2 generations of test chips. We have patented it. We have multiple papers published on it, and saving measured by silicon is significant in the range of 50% power saving. Thank you.